We really have just two more lectures worth of sort of formal new material. A lot of this course is, of course, very front loaded. A lot of things we try to get through relatively early on so that we have time here in the last month or so of this course to go back on anything that didn't quite make sense the first time, to have a chance to practice and hone in on the topics or parts of this first semester of chemistry that didn't quite make sense as much the first time around. Really, the way that I intend for you to sort of do your self analysis is with these badge tests, which will be have been graded. You can sort of see your results on Moodle, but I'll pass back and we'll talk about sort of what we'll do with these going forward. Uh, but really, this sort of first go at the first badge test is your personal inventory of what did I sort of understand very well the first time around, what needs to be reviewed, and sort of I will focus on in the second badge test, which will come in a couple of weeks. But overall, sort of my barometric gauge of how well the class is keeping up from semester to semester. Uh, Pretty happy with how people are doing this semester. And overall, the big takeaways from the statistics I've pulled for this class is that of the 13 badges passed, everybody passed at least part of one, so no one got absolutely 0 points from this first badge test go around. And most people sort of got the large majority of the available points. Obviously, there's still things that we can uh, amend our answers to round those up to the full pass. But most people are doing well and sort of progressing well. Of our badges, the first 13 or so here are in the first badge test. Our second badge test only encompasses 7 additional badges. So the bulk of this course is really here in your first shot. And based on sort of how much you've passed, you can kind of get an estimate of what you can kind of rest on your laurels a little bit of I've learned, I understand, I know how to do these things, versus things that we'll focus on for our second badge test. Uh, of course, there is going to be a second badge test in a couple of weeks to cover the last sort of third of this course's material. During that badge test, you'll have access to the same questions from the first badge test to continue working on anything that you didn't finish, to revise any incorrect answers to the first go around. So it is an iterative and cumulative process. Ultimately, again, trying to check off to make sure you know how to do the key concepts and the key skills we ask of you to have equipped yourselves with before you move into the second half of this course, which builds on everything that we learn here. Uh, I will pass out the tests graded at the end of this class. My general rule is that in order to sort of ensure that everybody has more or less the same amount of time and that you ultimately don't spend all of your time just whittling away and Googling answers, I hand back your badge tests. And you're welcome to sort of look at them. You're welcome to sort of take pictures and see what it is that you've missed and you need to study. But I will collect them back before you leave. And so they'll live within my custody, and I'll return those same badge tests to you on the second badge test for you to continue work from there. But I don't want you to holding on to them and continuing to work on them forever, since being efficient with your time and being quick with your answers is very much a part of being a scientist of some description. So I'll pass them out at the end and take note, make note of what you got right, what you got wrong, what you need to review for the second go around. There's ample opportunities coming up in the next few weeks for us to go over any concepts. I have some planned that many of us could use a refresher on. My sort of inventory of the different badges that people have gotten and ones that are still a little more elusive. Things like using electronegativity to predict whether we have a nonpolar, polar, or ionic bond. Uh, Most people are able to get it and figure out how that system works. A lot of things like significant figures. Many people sort of know a little bit about significant figures, but don't know the full, complete, valid rules, and so are missing some points here, only getting a partial pass, sort of 1.5 out of those 2 points. And some things like all the MO theory stuff, of course, is the hardest part of this course and requires, well, gives me some impetus to plan a more comprehensive review that everybody could enjoy and appreciate. So you'll be able to see sort of what you did and how you're currently doing at the end of this class. But take heart that everybody is making good progress, and I'm very happy with how everybody is gaining and picking up this understandably and admittedly very difficult material. By way of trying to prepare ourselves and round out the last third of this material, we'll sort of talk about what we may have missed 2 weeks ago when we talked about these chemical reactions, something that we've been practicing and exploring with our own two hands very much in the last two labs, was something that is helpful to review as we head into the last half of this course. So this process of going from, I can describe how atoms work and describe how they combine together to make molecules, and ultimately building towards the more difficult but more chemical thing of trying to predict how do these different molecules and chemicals interact with each other, and ultimately how do I predict when they change and what they change into, comes down to a lot of pattern recognition and some reasonable rules. In essence, a lot of what we do here in chemistry at this level is trying to predict things that are plausible, reasonable, could happen. It will take necessarily the second half of this course and much more schooling beyond that to be able to accurately predict 100% what actually happens in a given chemical reaction. For our purposes, we generally motivated first by seeing what has happened in the past. We do these chemical reactions in lab, we see a precipitate form, and then try to interpret the rules of why did that occur. What sort of general thing will help me predict if I see a similar reaction later on? How can I begin to recognize this pattern and predict plausible results, things that could possibly happen, and I know they happen because I saw them with my own two eyes. In general, the plausibility comes from our general rules of what makes a stable, reasonable molecule. Things like sugar, we know exists because we can look it up. It exists as a chemical structure. It has a name. It has a chemical formula. It has a Cas number. All these things that tell us this molecule does exist means that it's a very plausible, reasonable starting material, a reactant, and a very plausible, reasonable product that we might form. Something like C carbon H12, one carbon bonded to 12 hydrogen. We don't really have a name for. You've never really heard of it before. It doesn't have a Cas number, and it doesn't really follow any of the bonding pattern rules that we've looked at before. You'd have a very hard time drawing an MO diagram for CH12. You'd have a very hard time drawing a Lewis structure that satisfies the octet rule for CH12. Same thing for something like weird like CO6. So there's many things that we can rule out of ways that molecules will not recombine to make new products, but there are a lot of things that fall in between that are plausible, for which we require looking at some other reasonable rules. Our other reasonable rule that we tend to look at is that the weaker bonds, or we say the more labile bonds, will tend to break and form first. We saw this a lot in our precipitation reactions in our lab 4, in which we saw that for all of these precipitation reactions, we had different ionic compounds, things like sodium sulfate, Na2SO4. Sodium sulfate is a molecule, or a compound rather, that contains a lot of different types of bonds. There's an ionic bond between the Na plus and the sulfate polyatomic anion. This ionic bond is relatively weak compared to the covalent bond that binds the sulfur to the oxygen. And again, we predict this from the electronegativity rules that we talked about a few lectures ago. And we generally predict that this ionic bond will be broken and formed first before the covalent bond between sulfur and oxygen will be broken and reformed. So in all of our precipitation reactions, we saw that we may have rearranged and rebonded sulfate to a different cation, but we never saw a reaction, at least I hope we didn't see a reaction, in which we broke apart the sulfur and oxygen in the sulfate. And so we can generally look first at the ones that are going to be broken first and therefore remade or reformed first. And generally in this course, we see that the ionic bonds are the ones that are going to be messed with first. And then finally, of course, a lot of what we saw in our lab 4 again was pattern recognition. We see that an acid like HCl reacts with NaOH to give this acid-base reaction, we would predict a similar halogen acid. Instead of HCl, we move one element lower in the periodic table to get HBr. Cl and Br in the same column, same group, should behave very similarly. And so we would predict a very similar reaction for very similar chemicals. Hopefully now we have a little bit of a repertoire of chemicals and reactions we've seen in Lab 4 as well as Lab 5, but we'll continue to build this repertoire as we go along. Some of our library of different chemical reactions that help us to predict what will happen can be categorized in sort of three different types of reactions. We looked at precipitation reactions, going from two dissolved clear aqueous solutions to ionic solutions, and rearranging those ions to form a solid product, a precipitate, giving us a precipitation reaction, something we saw a lot of in Lab 4. We also looked at acid-base reactions, where essentially, in each of these, a proton, an H plus cation, a hydrogen cation is transferred from one acid to a base, all characteristic of this class or template of reaction. And then we also saw, particularly with the case of the metals, things like zinc and copper, these oxidation reduction reactions or redox reactions, in which instead of transferring an H plus or hydrogen cation, we really are transferring electrons of some number, in many cases going from a pure element, like a pure piece of zinc, to a zinc cation, zinc 2 plus, as it dissolves, corrodes, or rusts in an acid, for example. These precipitation reactions, we build upon sort of the patterns we've seen to predict when do we think we'll produce a solid, when do we think that we'll begin to see this type of change. We hopefully are able to recognize when we see these reactions happen in person, when we can identify a chemical reaction has occurred, forming a solid. In many cases, we are simply switching and finding the new pair of cation and anion, and a classic precipitation reaction happens when we form silver plus from silver nitrate, combined with the chloride minus, in this case from sodium chloride, to make silver chloride, which is a classic insoluble precipitate. A lot of our ability to predict this has to do with our ability to identify when will these ionic compounds form a solid. When will they not dissolve and form an aqueous solution? When will they be like silver chloride? In our Lab 4, we ourselves established many of these rules and many of these patterns. We saw things that we saw over time and time again, that silver with the various anions would form solids and precipitates. Things like barium and lead tended to form solids and precipitates. And we eventually group these into a series of rules that are reasonably sensible. We probably saw that anytime we had something with a sodium cation, Na+, so like sodium chloride, sodium nitrate, so on and so forth, as well as things with an ammonium cation, those complexes were always soluble. We never saw a solid form of sodium with something. Same thing when we had a nitrate, so silver nitrate always soluble, barium nitrate, lead nitrate, copper nitrate, so on and so forth, always form soluble compounds, were never are precipitate. In contrast, things that formed precipitates tended to be things like our barium or our lead or our silver, particularly combined with some of these other anions like sulfates. There's many other things that we saw. We saw precipitates form between lead and hydroxide, barium and hydroxide, silver and hydroxide. Those rules become a little harder to predict. And ultimately, there is a whole second half of this course that will give us even better rules to predict or at least understand their solubility patterns. But we can begin to see sort of the most obvious examples and begin to establish how do we understand and predict when we will form these solid precipitates and fill in the missing blanks to these chemical equations. One thing that helps us to predict as well is to, again, imagine these chemical reactions at their atomistic, molecular, or microscopic level. And when I say that these are aqueous solutions dissolved down to their homogeneous individual anions, it's helpful to remember and visualize that a solid chunk of sodium chloride, here as a compound, just sodium plus chloride minus. When we form a solution, we dissolve it or mix it with water. This mixture now breaks apart our sodium ions and our chloride ions to exist now as individual atoms floating around in this matrix or background of water. Because this solid crystal has now been broken up into individual atoms, we tend to not be able to see the sodium chloride anymore, since we have a hard time seeing individual atoms. So these solutions tend to look clear. They tend to look like there's nothing in them until we do a chemical reaction. This indeed is true of any ionic compound that is dissolved into an aqueous solution. That we break this ionic bond, our NaCl becomes individual Na plus floating around in our water, individual chloride minus atoms floating around in water. It doesn't break apart our covalent bonds, such as between the nitrogen and hydrogen in ammonium, or the sulfur and oxygen in sulfate, but still again breaks this labile, very weak ionic bond. Because when we look at these actual solutions in these chemical reactions, in which our sodium chloride isn't sort of a pair of Na and Cl, but rather individual Na plus and individual Cl minus, it allows us to rewrite our chemical reactions into what's actually floating around in our water, in our solution. And we see in many cases that some of our ions, such as sodium and nitrate in this particular example, don't really change fundamentally. They start as individual sodium cations, and they end up very much the same. In these cases, these spectator ions that don't really do anything in our reaction, they are there because they're part of the chemical, but they don't change fundamentally throughout the reaction. We tend to remove and represent this as a net ionic equation, which highlights sort of the working end or the business end of these reactions. What is actually the repeating pattern that allows us to predict that whether we have sodium chloride or potassium chloride, both of those should react with silver nitrate to produce a precipitate or a solid. In these cases, they all share the same net ionic equation, very much a pattern, once again, that we establish for ourselves and hopefully we're able to find in lab 4. The other type of reaction we looked at were the acid and base reactions. Again, the acid is a thing that transfers this H+. Some acids are going to be monoprotic, meaning they have one H+ to transfer. Some things, like sulfuric acid, which we saw in our previous lab, have 2 protons, 2 H+ that they can transfer, and phosphoric acid has even more. These combine with bases, which are anything that can accept an H+, and in many cases, our OH-, coming from things like sodium hydroxide, are a very classic base that we see time and time again that are able to accept H+ to form something like water, H2O. These acid-base reactions, again, always follow a very similar pattern. It allows us, again, to predict plausible, reasonable with the ways that they might work together and they might happen. We tend to see sort of 2 common repeating net ionic equations. One is in which our H+ combines with an OH- to produce water. This one's very hard for us to observe without the aid of something like an acid-base indicator. But we can also see a repeating pattern of something like an H+ transferred either to a bicarbonate anion, HCO3-, or the carbonate anion, CO3-, both of which can give us this carbonic acid H2CO3. We saw in our previous lab that this H2CO3 ultimately decomposes very quickly to give us CO2 gas, which we can observe by the fizzing and bubbling of these acid-base reactions. Again, these are patterns that we should see over and over again. They might be different acids, different bases, but they all share the same net ionic equation or the same pattern of reactivity. Even something complicated like baking powder, which combines a much more exotic calcium phosphate acid with sodium bicarbonate, baking soda, still follows down to the same transfer of H+ to the bicarbonate to make H2CO3, which decomposes to give CO2, which gives a lifting and the rise of baking powder, giving nice, soft, fluffy cakes. And regardless of which, whether we use one acid or the other, we see the same repeating pattern over and over again. A lot of chemistry, again, is pattern recognition, recognizing that even though these are more complicated molecules, the same mechanism, the same fundamental chemical transformation is a pattern repeated across a lot of different types of reactions. The final sort of template that we looked at and we reinforced in that lab are these oxidation reduction reactions in which we transfer electrons from one element to another. We likely were able to take a piece of zinc metal. Here is pure elemental zinc, even number, same number of protons and electrons. And if we mix that with a solution of copper sulfate or copper nitrate, we probably saw that the zinc got black, it probably got rusted. We saw a chemical change happening to the zinc. This came from the zinc transferring, losing 2 electrons, being oxidized, and those 2 electrons being picked up by the copper 2 plus in solution. That copper 2 plus gets reduced, gaining those electrons to turn from our copper 2 plus cation and turning into copper elemental metal. Because this reaction happens relatively slowly and at a relatively small scale, we probably didn't see a nice ingot of copper form, but we probably saw some sort of precipitate, which are really, really tiny particles of copper metal that if we were to melt them down would eventually form a nice solid chunk of elemental copper. Those redox reactions, transferring of electrons, can happen for many different types of metals. So again, silver as well can also undergo these oxidation reduction reactions. In many cases, we try to not only balance the number of each element on each side of our equation, adding these coefficients to balance this stoichiometry, but we were also aiming to balance the number of electrons. We see in this reaction between copper and silver, one which we may have run ourselves, that since copper gives up 2 electrons, we must have 2 parts of silver to accept those 2 electrons, since one silver can only accept 1 of those electrons. As a bit of nomenclature, we typically and have probably loosely used this term oxidizing or oxidizing agent elsewhere. And it really, again, comes down to the idea that one of our reactants is going to lose electrons and be oxidized. The other is going to gain electrons and become reduced. We may also say that the thing that gets oxidized is a thing that reduces something else. So zinc might be called the reducing agent. It gives electrons and gives electrons to something else that we call the reducing agent or reductant. And copper 2 plus we would similarly call the oxidizing agent or oxidant, since it's a thing that oxidizes the zinc. So there's a nice parity there. And it really again reflects where are the electrons coming from, where are they going, and how do we name those appropriately. In many cases, most of the oxidation reduction reactions we've done in this class have to deal with metals, which is easy to see zinc elemental zinc turning into zinc 2 plus. But these redox reactions also extend to non-metals, and quite importantly, for things like combustion reactions. In this combustion reaction, reacting methane plus elemental oxygen, O2, burning natural gas, we see that we get a chemical change. Our bonds are broken, remade into CO2 and water. This may be hard to recognize as one of our types of reactions. It's not really an acid-base reaction. It's certainly not a precipitation reaction. And in fact, at its core essence, it is an oxidation reduction reaction, though it might be harder to observe. In many cases, even if we don't see specific change in the formal charge, zinc 0 going to zinc 2 plus, we can still track the gain and loss of electrons by something we refer to as oxidation numbers. These oxidation numbers help us track sort of the formal charge, even if it doesn't have an ionic charge. We do so by looking at how are these electrons shared, how are these electrons balanced per atom. Things that are pure elements, for example, we would refer to having as an oxidation number of 0, since they have the exact number of electrons as protons as they exist as pure elements. So each of these oxygens has an oxidation number of 0, sort of a formal ionic charge of 0, since it doesn't have any excess or deficit of electrons. Anything as an ion, of course, has already its ionic charge, which we look at as an oxidation number. For everything else, for all these other non-metals, we sort of have two tried and true rules based off of the high electronegativity of something like oxygen versus the low electronegativity of something like hydrogen. Typically, when we see these non-metals, we can always automatically set any oxygen bonded to something else. So for example, this oxygen bonded to carbon in CO2 as having a -2 charge. It is not technically a -2 anion. We can still assign it to be an oxidation number, effectively having 2 extra electrons. And we typically refer to H as having a +1 oxidation number, again, because it's always slightly positively charged in many of these covalent bonds. With that, we can begin to assign where these electrons are moving based off of these sort of invisible oxidation numbers. If we were to look at this carbon in CH4, because it has 4 hydrogens bonded to it, each of these 4 hydrogens sort of holds an invisible +1 charge, meaning that this carbon starts out with a -4 oxidation number, not quite an ionic charge, not quite a -4 anion, but in the bookkeeping of redox reactions, we consider it begins with a -4. This oxygen begins as 0 since it's pure elemental oxygen. When we recombine them, we know that electrons must have shuffled between the carbons and the oxygens because our resulting products are CO2. Our carbon that started as -4 is now bonded to 2 oxygens. Each of those 2 oxygens, being very electronegativity, carries a -2 oxidation number. And that means that this carbon must have changed to a +4 oxidation number. You can kind of think of it, not formally, but you can kind of think of it as this carbon going from a -4 carbon to a +4 carbon. To do so, it must have lost 8 electrons, undergoing an oxidation. So we would refer to that methane, with sort of a -4 carbon, has to be oxidized, losing 4 electrons to turn into this CO2. For everything that is oxidized, something has to be reduced. So this O2, starting as 0, and eventually moving to -2 by being bonded to hydrogen and carbon, both of which are less electronegativity, had to go from 0 to -2, so had to be reduced, gaining those electrons. One reason why we typically call oxygen an oxidizing agent or an oxidant, or hence the name oxidation, is that whenever we react with oxygen, it will typically gain electrons, ripping those and removing those electrons from something else. This reaction very much follows a pattern that oxygen is an oxidant. Oxygen will oxidize methane, taking the electrons from methane and turning into something else. Oxygen will oxidize methane by removing 8 electrons, going from a carbon with sort of a invisible -4 charge to a carbon with a invisible +4 charge from methane to CO2. In many of these cases, a lot of these patterns, again, repeat themselves. We usually see that when things are combusted or burned or react with oxygen, oxygen acts as our oxidizing agent. It is reduced. And the other thing, in this case methane, or quite often another fuel or hydrocarbon, is going to be oxidized, producing heat, and of course producing things like CO2 and water. Now, in addition to a lot of the pattern recognition and trying to predict what reasonable chemical reactions look like, the other big important part about these equations is the fact that we balance them, that we have these coefficients that help us not track just that methane reacts with oxygen, but importantly that 1 mole, 1 molecule of methane produces 1 mole or 1 molecule of CO2 and requires 2 moles or 2 parts of oxygen to do so. For that, we of course need to be comfortable with converting between things that we can measure, masses and volumes, to things that we can count, moles or atoms, because ultimately the ratio of these reactions, how much of each reactant is required and how much product is made, goes on a mole-to-mole basis, not a mass-to-mass or mass-to-volume basis. For that, we have 2 types of conversion factors we use time and time again. The molar mass, which helps us convert between a mass we might measure and counting a number of moles. We did this ourselves a lot, of course, with our last titration lab, in which we measured the mass of our phthalic acid. And because we knew the mass of that phthalic acid, we could count how many moles of acid, how many moles of H plus could be transferred in an acid-base reaction. We also, of course, need to use something like a molarity, a moles per liter, represented by a big capital M standing for molar. And this molarity helps us to convert volumes we might measure into a number of moles we might count. We also did this in our titration lab. We measured the volume of sodium hydroxide solution, and the concentration of that solution allowed us to count how many moles of NaOH reacted with a certain mass or amount of acid. This is something that requires practice, and again, we sort of see the same types of problems over and over again, but there's a very helpful map in your textbook, which we replicate here, that helps you decide and figure out how to convert from something you might measure, such as the volume or mass of a particular reactant or product, converting that to the equivalent moles of that particular reactant or product, using this stoichiometric ratio, how many moles of A react with how many moles of B, before we convert that again, once again, to something that we can measure. As a way of practice, we'll go through one example that we covered towards the end of last class, but it's worth repeating. This is, of course, very helpful as we look at problem set 4, which once again has us not only interpret chemical reactions and write reasonable ones, but as well as deal with the quantitative side of asking how much reacts, how much do we produce. The example that is quite relevant, and maybe the chemistry that you might actually do in your real lives outside of class, is the production of soap through the process called saponification. This chemical reaction takes something like an animal fat, which we represent by the molecule stearin, and you mix that with a base, sodium hydroxide, also called lye, and you produce the two components of soap, which are going to be glycerol and sodium stearate. Sodium stearate is sort of the business end of the soap. The glycerol there is really just a byproduct, but helps serve the hand feel of soap as well. Even though these are complicated, large, big molecules, we can still reduce them down to a relatively simple chemical equation. One thing that has already been done for us is to balance this equation to make sure we start and end with the correct number of each element. We start with and end with the same number of each carbon, hydrogen, oxygen, and sodium, reflecting that one molecule of our stearin requires 3 moles, or sorry, 1 mole of stearin requires 3 moles of sodium hydroxide to produce 1 mole of glycerol and 3 moles of our sodium stearate. It's not a random arbitrary amount of soap that you can make from a particular amount of animal fat. And if you were a soap maker, you may want to know, if I start with a certain amount of fat or oil, how much soap should I expect to produce? Our calculations might follow that if I start with 1 gram of my stearin and my animal fat, and I'm able to completely convert that into all the soap products, my sodium stearate and my glycerol, how much soap should I end up with at the end of the day? For that, we need to calculate how many grams of my product, each individually, would I produce from 1 gram of my stearin. From that, I take my measured thing, 1 gram of stearin. I have to convert that to a number of moles of stearin, so I'll use the molar mass of stearin to go from mass of stearin to moles of stearin. I then invoke my stoichiometric ratio that says that for every 1 mole of stearin, I produce 3 moles of sodium stearate. I convert that once again back from moles of sodium stearate to grams of sodium stearate with a molar mass. And I see that from this chemical reaction, I produce 1.03 and some balance of this particular soap molecule. Using my 2 conversion factors, my molar mass and my stoichiometric ratio, canceling units as I go along to make sure that I haven't forgotten anything. And I'll do the same thing for my glycerol, again invoking this stoichiometric ratio of a 1-to-1 from stearin to glycerol. Combining those together and accounting for significant figures, including the ones that we did in the titration lab, work under the real assumption that it's almost impossible to exactly nail, exactly head on the exact right ratio of reactants to reactants. When we ran our titration, we probably got the very real hands-on experience of trying to exactly react the exact right number of atoms or molecules of acid with base. We saw that our titration turned from clear to pink very quickly within a single drop of our base solution, reflecting that this ratio is very, very hard to practically hit exactly on the head. In most cases, we're going to have slightly more of one reactant than the other. In those instances, we would refer that we are going to have one limiting reagent, one thing that is going to be slightly under the exact right ratio, and one thing or several things, everything else is going to be in excess. In many cases, or rather in our titration labs, we saw that we started with a limiting amount of acid, and we added our base just after we passed this 1-to-1 ratio. So our base was in slight excess, but still more than the exact right ratio. Because we assume that there's always going to be a little bit of imperfection in these chemical reactions, it's important to make sure that we pick the correct reactant or understand which reactant is going to be limiting, is going to run out first, and which one's going to be in excess. In the case of our soap reaction, it's quite important that between our two reactants, animal fat, which is not particularly pleasant to rub on our hands, but not dangerous, it's important that we pick and make sure that our animal fat, our stearin, is going to be our limit, or is going to be in excess. And our sodium hydroxide, our lye, our caustic thing that will burn your hands and burn your skin, is going to be in limiting reagent. We want to make sure all the sodium hydroxide gets used up and that there's going to be a little bit of our stearin left over if of those part two reactants. And so we can calculate how do we guarantee that all of our sodium hydroxide is used up, is a limiting reagent, and that our stearin is going to be left over, making this soap safe for us to use. We could potentially look at a sample recipe, one that exists from other people, and to check whether or not this is a safe recipe for us to use, look at between our stearin and our sodium hydroxide, these two very random looking rounded masses that we're given. How do we guarantee that this is a safe combination, that we will have excess stearin left over, and all of our caustic, dangerous sodium hydroxide will be used up? For that, we can calculate how much stearin is used if we use up all of our sodium hydroxide, as also we can look at how much sodium hydroxide is used up if all of our stearin is consumed. In these cases, we can sort of guess and check between the two. In this case, I'll look at my stearin, and I'll say that if all my stearin gets used up, if my stearin is my limiting reagent, my 10 grams converted to an equivalent number of moles, the mole ratio of 3 moles sodium hydroxide to 1 mole sodium of stearin, and then back to the mass of sodium hydroxide with the molar mass, I'll see that my 10 grams of stearin requires 1.35 grams of sodium hydroxide. Because I only have 1 gram of sodium hydroxide, that means that my sodium hydroxide will run out, will be used up, will be the limiting reagent before my stearin gets used up. This means, of course, that my sodium hydroxide will be my limiting reagent, my stearin will be in excess, giving us a safe soap that will have no caustic chemicals in it, and a little bit of a hydrating animal fat built in there as well. This process and most soap recipes are going to be following this same type of ratio, which is often called superfatting. Again, building an idea that it's going to be nearly impossible to get the exact right ratio down to the exact molecule of stearin and sodium hydroxide. So the error on the side of caution, I can calculate how to guarantee all of my sodium hydroxide will be used up by having excess amount of stearin left over. In practicality, what it means is that not all of my stearin, my 10 grams of stearin, will be converted to soap. And I can calculate based off of my limiting 1 gram of sodium hydroxide. If all that gets used up and converted to soap, I should get 7.43 grams of my stearine converted, meaning that maybe 25% of my starting material will be left over. In problem set 4, we have opportunities to practice both sort of the interpretive side of chemistry, going from a description and writing a chemical equation, balancing them, making sure things are the appropriate phases, as well as calculating things based off of those stoichiometric ratios. If I start with a limiting amount of one molecule, how much product should I produce? How much of my other reaction will be left over? So on and so forth. Now, where we go from our chemical reactions really kind of dives back into maybe a more fundamental question in which we examine what are things made of, and how does this matter interact with each other. And a question that may have occurred to you at some point before now is that we describe very succinctly and we describe very precisely that a covalent bond holds hydrogen and oxygen together. We can draw MO diagrams, we can draw Lewis structures and show that there's a bond, a set of shared electrons that hold the hydrogen and oxygen within one molecule of water together. But the question is, of course, that when we look at a glass of water or a rain cloud, that our molecules of water are in the billions and trillions and quadrillions, and they don't exist as sort of randomly free whizzing molecules. They cluster together as a droplet of rain, as a cube of ice. And the question is, what is that attractive force that holds different molecules together? They're not bonded together in the same way that hydrogen is bonded to oxygen. We know that those covalent bonds are very, very strong and very, very hard to break and remove and tear apart. The bonds, or whatever force holds these molecules of water together, have to be a lot weaker, but still present, still measurable. So we typically refer to the bonds, things like ionic bonds or covalent bonds, or the metallic bonds we reserve for more advanced classes in chemistry, as being sort of in an energy range of several hundreds to several thousands of kilojoules, this measurement of energy, per mole, to give us sort of a reference point for how strong this force that holds hydrogen to oxygen together. These covalent bonds we might refer to as intramolecular forces, representing forces within a molecule that hold a molecule together. The other type of thing that we have to consider is an intermolecular force, a force that exists between molecules. This inter versus intra, you may sort of best remember by the idea that interstates are roads and highways that go between states. And similarly, intermolecular forces are whatever forces hold one molecule of water to another molecule of water and the trillions and billions from beyond there. This is a topic you'll cover a lot more in the second half of this course, but we'll sort of seed it now so you hear it once and have time to ruminate on it, that there's a bunch of different forces in varying degrees and shades that are very, very weak. If the strength of the bond between hydrogen and oxygen is hundreds to thousands of kilojoules, there is a much weaker but still measurable force in the range of tens of kilojoules that holds one molecule of water to another molecule of water. These intermolecular forces come in a number of varieties, and one reason why we spend a lot of time looking at these structures and ultimately the polarity of molecules is it helps us to identify which types of forces we have present that we'll talk about briefly to get some orientation, but you will revisit in greater depth in the second half of this course. The weakest force that holds a molecule of water to another molecule of water we refer to as the London dispersion force, or the dispersion force, or the momentary dipole. This exists as really a very weak and fluctuating force that is true of all matter. All molecules have this London dispersion force. And it comes from the idea that in our combined set of orbitals, this cloud of electrons surrounding our atoms and our bonds, that this cloud of electrons, once again, is sort of a wave as much as they are particles. This sort of spherical wave of electrons surrounding a molecule, such as methane shown here, like waves do, will tend to oscillate and to shift. As this electron wave and density oscillates and shifts, you get sort of momentary imbalances, like people rocking a boat side to side. While on average, if you rock a boat side to side, it's not going to move in the water, it's simply going to tilt left and right. But each of those rocking creates an imbalance in those positive negative charges. And what you get is a very, very weak, very, very momentary, slightly positive side, slightly negative side. Even for a nonpolar molecule like methane that has no net dipole, you still get a very, very weak momentary fluctuation from this rocking of electrons that creates a slight attractive force between one molecule of methane and another. This force is very, very weak, but it does scale with mass, since the larger molecule, the larger molecule, the more larger molecule, the more electrons you have, the larger your boat you have, the more people can rock side to side. And as you get more electrons, this temporary force can become stronger and stronger, such to the point where something like a solid chunk of graphite, the material in your pencils that creates these markings, these solid chunk of graphite is held together by these London dispersion forces, these very, very weak bonds, or very, very weak forces between molecules of these carbon graphene sheets that are strong enough to hold a solid piece of pencil lead together, but weak enough that when you rub that lead against a surface of the paper, rubbing that surface breaks this weak London dispersion force and deposits some of your lead, some of your graphite onto your paper, leaving a mark. This weak force, of course, while being everywhere, is ultimately a very, very weak one. And we often care when we start to begin dealing with polar molecules, ones that have these net dipoles. Again, you'll learn more about the consequences of having a polar molecule that might exhibit a dipole force in the second half of this semester. But quite intuitively, for any polar molecule, such as this molecule of formaldehyde, which features a slightly positive carbon side and a slightly negative oxygen side, this net dipole pointing from the carbon to the oxygen creates an attraction, like a bag or a bunch of different magnets, in which the slightly negative end of one molecule of formaldehyde has a very slight attraction to the slightly positive end of another molecule of formaldehyde. This stronger attractive force, stronger than the London dispersion force, of course, only exists with these polar molecules that have net polar bonds, but it creates a slightly stronger, stickier force between these different molecules of formaldehyde. In many cases, the strongest type of polar bond that creates the stickiest attraction between different molecules is what we refer to as the hydrogen bond. It is still not quite a bond. It's not as strong as a covalent bond. But the fact that oxygen has such a different electronegativity, such a strong dipole compared to hydrogen, means that this polar interaction between the oxygen, the negative end of one water molecule, and the hydrogen, the positive end of another water molecule, is a relatively strong intermolecular force that makes water relatively sticky with itself. This means that our water molecules are attracted to each other and are one of the reasons why we have nice sort of cohesive droplets of water as they fall from the sky. Each of these water molecules is attracted to the other because of this slightly positive side of our polar molecule and the slightly negative side of another polar molecule. These hydrogen bonds you'll talk more about in your second half of chemistry, as well as in your biology classes as well, since this type of intermolecular force, this hydrogen bonding, underlies the DNA base pair recognition found within each of our chromosomes and each of our strands of DNA. The final intermolecular force, once again quite sensibly, is a strong attraction between the polar end of a molecule like water and the fixed sort of poles of a cation or anion. One of the reasons why sodium chloride does dissolve in water, and it's very hard to remove the sodium and chloride from water once it's dissolved in there, is that our Na plus has a very strong attraction to the negative end of our water molecule, and our chloride minus has a very strong attraction to the positive end of our water molecule as well. These intermolecular forces, once again, still no more mystical than positive charges attracted with negative charges, are another force for us to be aware of that complicates not just how an individual molecule behaves, but how a collection of molecules, as a glass of water, as a rain cloud, as a ocean of water, behaves and indicates some of their reactions. These mixtures, of course, we've seen and experienced with our own two hands in our last two labs, and a lot of the weird properties, uh, and a lot of the things that come as a consequence of the fact that Na plus is not just randomly mixed in with water, but has an attraction between the positive and negative charges, is again something that requires another semester of chemistry for you to dive in fully. Now, with any hope, as my screen reconnects, it's helpful again to remember that these intermolecular forces aren't nearly as strong as our bonds. Our intramolecular forces, ones that exist within molecules, our covalent bonds, ionic bonds, as well as metallic bonds, are very, very strong, much more dominant, and dictate a lot more chemistry that we focus here on this first semester. But it is still helpful to keep in the back of your mind as we go forward that our molecules are not just floating around and bouncing around without any attraction to each other. There are forces that hold water molecules to water molecules, sodium ions to water molecules that we will expand on in subsequent semesters. One of the most important places that these intermolecular forces come into play is trying to understand why does water at room temperature exist as a liquid? Why does it require us to heat it up to turn into a gas, to turn into steam, or to cool it down, turn it back into a solid? Why does water exist as a liquid at all these at room temperature versus something like methane? Natural gas exists as a gas at room temperature. In many of these cases, these different phases of matter are dictated by these intermolecular forces. When we have a solid, depending on how strong those intermolecular forces are, our solid is dictated by strong intermolecular forces that hold one water molecule to the other. At very, very cold temperatures, each molecule of water doesn't really have a lot of energy to move and bounce around, and so become locked in place, rigidly bound in place uh, into the crystalline lattice of our cube of ice because of these strong intermolecular forces between our polar water molecules with strong hydrogen bonding. Now, as we add energy, we begin to heat up from a cold temperature to a warm temperature. We begin to add energy to these molecules of water. As we add energy within a chemical sense, it causes these molecules to begin to vibrate and to rotate a little faster, vibrating and sort of moving in place. And as we begin to add energy, they now have enough energy to try to sort of twist out of place to be able to momentarily break free from the strong intermolecular forces. You might think in the way that we here on Earth are bound by the force of gravity to be close to the ground. And if we're very tired, we don't have a lot of energy, we probably are very much firmly rooted on the ground. But with enough energy, with a little more spring in our step, we are able to leap off the ground, resist momentarily this force of gravity, and separate ourselves and move and translate about. That's sort of the same picture with water. As water, or any molecule, gains slightly more energy, we're able to momentarily resist these intermolecular forces that hold water molecule to water molecule and allows it to temporarily move and shuffle and find a new position. This is what gives water the ability to move and slide around itself, for it to flow and to reorganize itself. It's still held together. This collection of water molecules as a liquid are still collected together as a droplet, but they're able to move around each other because of slightly more energy that can allow them to resist, temporarily leap over these intermolecular forces. At the very far extreme, if we have a lot of energy, uh, let's say if you were to strap rocket boots onto your feet, we have enough energy that we're able to completely break free of these intermolecular forces in the same way that we would be able to be free of the force of gravity and allow to go wherever we would like. In the gas phase, our molecules are effectively completely free of these intermolecular forces, have enough energy to zoom past each other without being attracted to each other because they have enough of a kinetic energy to them. This gas phase is typically the one we start talking about most in most chemistry courses, largely because it allows us to ignore the bulk properties of these intermolecular forces at high enough temperatures, at sufficiently low pressures. Each of these molecules do exist somewhat independently, but once we begin to cool things down, once we begin to increase pressures, these intermolecular forces become a lot more concerning, a lot more important for us to consider. So in this first half of this chemistry course, we typically start by talking about the gas phase, uh, allowing us to revisit these intermolecular forces a little later in this course sequence. When we talk about things in the gas phase, we once again probably have a relatively decent intuition for what gases are like. But on a very precise atomistic, molecular, and chemical level, when we talk about the gas phase, we imagine in our head a bunch of particles, be they atoms or molecules, small molecules, large molecules, are all floating around and moving very, very quickly and randomly through a volume. Within the air that we breathe, we have nitrogen molecules whizzing around, moving around randomly, free from each other and independently through the air that we breathe. Same for the oxygen and CO2. We typically consider that for these gases, that the size of a molecule is much, much smaller than the space between those particles. Gases, as you probably have a good intuition, are pretty empty. There's lots of empty void space without molecules, without matter. And much like stars throughout the galaxy, our particles are there, but a very, very low concentration compared to a much more densely packed solid or liquid. We typically refer to how quickly these particles are moving, how much energy they have to resist these intermolecular forces, by their temperature. Their temperature, or the temperature related to any substance, is really an average of how much kinetic energy, how quickly those particles are moving. Something very, very cold, like a cube of ice, has very low kinetic energy, very low velocities, very, very low speeds, not moving at all, or not moving very quickly, in some instances not moving at all. As things get hotter, we refer to that as having an increase in kinetic energy, increase in velocity. Our particles in our air, being in the gas phase, are moving around very quickly. Lots of kinetic energy, lots of speed, lots of movement. The other property which we refer to gases is the pressure. As every gas molecule is zooming around through the air that we breathe, they're hitting different surfaces. How often they hit those surfaces and with how much force they hit those surfaces, we can measure and quantify as the pressure of that gas. This unit of pressure, a way to measure how strongly each molecule is hitting our cells, every surface, we typically refer to with several different units here in chemistry. You typically will use the unit of an atmosphere, ATM, to refer to the pressure in chemistry. Conveniently, the pressure at sea level from most experiments occurs at 1 atmosphere, one sort of sea level atmosphere of pressure, referring to the amount of gas and the force at which those gas molecules are hitting surfaces. We may also from time to time use other units of pressure such as mmHg, which stands for millimeters of mercury, another unit of pressure, as well as torr, pascal, or bar, all of which are ways that different fields of chemistry or subfields refer to pressure, but also referring to the same idea of trying to equate how much of a gas is there, how often are they hitting a surface, and what does that tell us about that molecule in nature. Most of our discussions with gases are going to deal with these gases that do behave as if they don't have any intermolecular forces, that allow them to be pretty independent from each other, whizzing through the air very, very quickly. We refer to this type of gas as what we would call an ideal gas, largely because it behaves a lot of very easy and very clean mathematical formulas. It allows us to predict the properties of that gas based off of some measurable things. The ideal gases, which are many gases, particularly ones that are at sort of normal moderate pressures, things within 1 atmosphere plus or minus a few ATMs, as well as at normal moderate pressures. Most of the air we breathe we can refer to as an ideal gas, largely for the reason that it behaves what we call the ideal gas law. This ideal gas law, which you may have come across in physics, is a very simple one that says that there's a linear relationship. There's a one-to-one relationship between these 4 variables and 1 constant. These variables are P, standing for pressure, usually referred to in units of atmospheres. The volume, V, usually measured in liters as helpful units. N here refers to the moles of gas, the number of moles of gas, of course, using the unit of a mole. R is a constant, called the ideal gas constant, that is there to mathematically relate the pressure of a gas to the volume of that gas, to the number of moles contained in that volume, to the temperature or the energy of that gas. The temperature is the one unit that requires some special attention, largely because it uses this unit of K, standing for Kelvin. While in most of chemistry we will use units of degrees Celsius, since it's a reasonable metric unit, we typically use and must use this unit of Kelvin, which the conversion from a temperature in degrees Celsius to the temperature in Kelvin is done by adding 273.15, very specific number, is done so that all of our temperatures are going to be positive numbers. In units of degrees Celsius, we can have negative degrees Celsius on a very, very cold day. In very, very frigid parts of the world, we can get down to minus 10, minus 20, minus 30 degrees Celsius. And this particular equation doesn't deal well with negative numbers, since it would make things like the number of moles a negative number. We don't have negative numbers of moles. And so we make this adjustment, adding this 273.15 to turn all temperatures in chemistry into positive numbers to be something above the value of 0. So with that one specification, we otherwise have an equation that helps us and quite easily relate the pressure, volume, number of particles, and the temperature of a gas with a measured constant. In this case, that is a very well-known 0.0821 liters times atmospheres divided by moles divided by Kelvin, a scaling constant that relates these 4 variables. Now, one thing I want you to notice about this ideal gas law is that this ideal gas law equation describes any ideal gas. And I've made no mention of what an ideal gas looks like chemically. And indeed, if we look at this ideal gas law, we'll see that it doesn't really care about the identity of the molecule. Whether we have an ideal gas like helium, found in a helium balloon, or nitrogen gas found in the air around us, or CO2, even though all 3 of those types of gases are very chemically different from each other, one's a pure molecule, one's a pure element, the other 2 are covalent compounds, one's CO2 is much larger and heavier than nitrogen. All of these three gases are ideal gases that all follow this same equation, that all relate these four properties with this one equation. This ideal gas equation doesn't care about the identity of these gases because within an ideal gas, tiny particles zooming through the atmosphere, moving relatively independent of each other, they all look like same sort of tiny particles and all behave very similarly, of which the only thing that I care about and the only thing I need to take into account is the number of molecules, the number of particles whizzing about. Within an ideal gas, one reason why we start here is because they're quite well behaved, is that helium molecules, or an atom of helium, behaves as a gas the same way a molecule of CO2 does. They are, of course, heavier than each other, but as far as the pressure, the force they exert by hitting a surface, the volume they occupy, and the temperature or energy with which they move, all three of those ideal gases behave identically to each other. It's quite convenient because it allows us to do a lot of different calculations with a wide variety of gases. And like any equation, our ideal gas law really is an equation, something that we can plug in variables to and solve for unknowns. And really, this equation has four variables: pressure, volume, number of moles of gas, and temperature, as well as one constant. And if I can measure or know the value of three of those, I can solve for the remaining unknown one. So if I know the pressure and the volume and temperature of the gas in this room, the air in this room is at 1 atmosphere. There's several hundred liters of gas. We could measure that. And the temperature is at a very nice room temperature, maybe slightly warmer on some of these days. If I know the pressure, volume, and temperature of a gas, things I can measure, I can convert that and count how many moles of gas are found within this room. This ideal gas law, in essence, is a type of conversion factor, the same way that we can convert a volume of a solution to a number of moles with the concentration, or the mass of a solid to a number of moles with the molar mass. We can similarly convert and calculate the number of moles of a gas if we can measure these three other properties. The final thing that we have to pay attention to is that this equation is very, very much based on unit agreement on dimensional analysis. As I mentioned previously, our temperatures must always be in units of Kelvin, or else we'll have negative temperatures that make negative numbers of moles of gas or negative volumes, which doesn't make sense physically. And we have to pay attention to make sure that our units of pressure, volume, and temperature cancel out with whatever value of R we have. In many cases, keeping it in atmospheres, liters, and Kelvin is sort of the easiest way to deal with this ideal gas law. So what do we do with this ideal gas law, and how does it help us really understand the properties of these gaseous substances? In many cases, we don't necessarily need to know all of the properties of this gas to be able to understand how the properties will change. In many cases, we often use the ideal gas law in a relational sense, meaning that we know that if we keep some of these variables constant, we don't change the pressure, we don't change the volume, we don't change the temperature, then we can relate the other ones based off of a equivalency. In many cases, we can take the full ideal gas law and say that if we don't have a change in n, that at the beginning of if I were to say blow up a balloon, I fill this balloon with an amount of gas, my own breath, some helium, air. That volume of that balloon is a sealed off volume. I know within that balloon that the number of moles of gas isn't changing. No gas is entering that balloon, no gas is leaving that balloon. I know n is constant. Now I can say if I take that balloon and I were to squeeze that balloon down, I can change the pressure and volume of that balloon by squeezing it down. I might want to predict how will the temperature change if I was to squeeze and compress that balloon. If I was to heat that balloon, how will the pressure and volume change in response to some sort of perturbation? For that, we often use this relational version of the ideal gas law that says that the pressure, volume, temperature at an initial condition and a final condition, state 1 versus state 2, is related by the ideal gas law, here setting n equal to each other if my number of moles of gas doesn't change. It builds upon a lot of intuition we may already have about how gases behave. So for example, if I was to take a container, in this case a piston, and I was to seal this piston, by sealing it, that means I don't change the number of gas molecules found within this little canister. It is sealed so N remains constant. If I was to take this canister that starts at ambient pressure, 1 atmosphere, and a volume of 2 liters, if I were to physically compress this cylinder down, compress this piston, and shrink the 2 liters down to 1 liter, as I press it down, I must know, and I can calculate, that as I keep N constant, and as I keep the temperature constant, my pressure and volume must change inversely. If I have my volume, I have to double my pressure. If I shrink the volume from 2 liters to 1 liter, my pressure must increase from 1 atmosphere to 2 atmospheres. Similarly, if I was to instead take my sealed piston and I were to let it adjust to ambient 1 atmosphere, and I was to heat this canister from 200 Kelvin, doubling the temperature to 400 Kelvin, my volume of gas should expand, going from 1 liters to 2 liters. In that process, I see once again that my temperature and my volume at constant pressure, I'm not restraining the pressure, those are directly related. I double the temperature, I double the volume. And this, again, should hopefully match some intuition we have about how gases behave. As we boil something, we increase the temperature of a sealed canister, maybe a can of soda. As we boil it, we increase the volume of the gas as we heat it up, relating to this very predictable ideal gas behavior. Finally, other variations say that if I was to, again, just keep the volume constant, I was to hold this piston in place. If I were to increase the temperature, doubling the temperature from 200 Kelvin to 400 Kelvin, by keeping the volume constant, I must know that my pressure must double in response, since all these are related by this sort of very much one-to-one directional relationship. Pressure and volume inversely related, pressure and temperature, and volume and temperature directly related. As one doubles, the other must double as well. In many of these cases, we use this idea to try to predict what happens as we undergo chemical reactions. If I heat something up, how does my volume of my gas change? If I increase the number of moles of gas, how does my pressure, volume, and temperature respond accordingly? Another consequence of the ideal gas law, as I noted before, the ideal gas law tells us that it doesn't matter the identity of my chemical species. Helium, nitrogen, and CO2 all behave identically as ideal gases. What that means is that conveniently, when I have a mixture of different gases, such as air, which contains 80% oxygen, or 80% nitrogen, 20% oxygen or so, that each of those ideal gases, nitrogen and oxygen, must behave identically to one another. It allows me to break apart my ideal gas law not into one that just describes the total behavior of all the air, but describes each individual species equivalently. This subscript I refers to one species within this ideal gas mixture. It says that the pressure of just the oxygen times the volume of just the oxygen is equal to the number of moles of just the oxygen found within this air mixture. Temperature, being an intensive unit, is the same for all molecules, but it allows me to do some very quick conversions between gas units. If I was to say and take my air mixture that is roughly 79% N2 and 21% O2, this percentage, this ratio, refers to a number of different types of ratios and concentrations. It might refer to, equivalently, that the partial pressure of the nitrogen is 79% of 1 atmosphere, or 0.79 atm. And the partial pressure of oxygen, the fraction of the total pressure just coming from the oxygen molecules, is 21% of the 1 atmosphere here at sea level, or 0.21 atmospheres. Because all these are directly related in a 1-to-1 ratio, it also means that if I had to have 1 liter of air, that the partial volume of that 1 liter is 79% nitrogen, 0.79 liters N2, and the partial volume of oxygen is 21% of that 1 liter, 0.21 liters. It also means that at a molecular level, that if I had 1 mole of air, that 0.79 moles, or 79% of that 1 mole, is N2. 21%, or 0.21 moles, is oxygen. Well, again, one reason why we use ideal gases and we talk about them first is that it makes a lot of conversions quite simple. Because the ideal gases don't differentiate between N2 and O2 as being different size particles, different shaped particles, allows us to do very quick conversions between things we can measure, volume fractions, pressure differences, to a thing we can count, and ultimately a thing that we as chemists care a lot about, the number of moles or number of particles of each of these chemical species. One thing to be careful about, of course, is that these different molecules, N2, O2, helium, still are different masses. And so typically when we look at these volume fractions, 79% N2, 21% O2, they will refer to as a pressure percentage, a volume percentage, or a mole percentage, and that will be different than a mass percentage, which of course, since these are different masses, gives us a different weight percent. By mass, air is about 23% oxygen versus 77% N2. Slightly different again because they are still different masses. But as far as their pressure, volume, and temperature is concerned, this N2 and O2 molecules do exist and behave identically to each other. Now, most of our work here with the ideal gas law is going to be things that we practice, of course, in problem set 4, as well as things that we will work with on Wednesday, trying to do a couple of things. On Wednesday, we will look at, 1, do we trust this ideal gas law? As I've repeated before, you should always enter science with a bit of skepticism, that we tell you these things, and we show you fancy pictures, and we say it authoritatively, but you really shouldn't take it wholeheartedly until you've had a chance to run an experiment yourself and verify that these equations are true, that these behaviors and phenomena we see are real. And so on Wednesday, we are going to run experiments to verify ourselves that this ideal gas law is true, that these relationships are true, and that our constant we calculate matches the one that scientists have put before us. We will also use this ideal gas law as a tool, ultimately trying to use the measurement of pressure, volume, and temperature to calculate a number of moles. In particular, on Wednesday, we will look at how do we measure the molar mass of a gas. We can measure the mass of a gas quite easily, but how do we count how many moles per that 1 gram of gas? For that, we have to use the ideal gas law, once again, as a conversion factor between things we can measure, the volume of a gas, and the number of moles of that gas we suspect are in there. This week's problem set 4, covers both elements of the chemical reactions we talked about in the last 2 weeks, as well as this work newly with the ideal gas law. Our remaining time here, and the remainder of our session, which luckily will end with ample time to do whatever we find useful. Our remaining time is I will pass back any sort of graded work. As I mentioned at the beginning of this class, I'll pass back your badge tests. Now, as I said before, the badge tests are graded, of course, and you should take a look at what you've gotten right, what you still are working on and in progress for. These badge tests, of course, are also on Moodle to indicate what you've passed fully, what you've passed partially. These badge tests you're welcome to look at, you're welcome to study, you're welcome to take pictures, take notes, make whatever sort of documentation you need for your own review purposes. while you are here in class, but I will collect them before you leave so that you don't have an infinite amount of time to work on them without my supervision. Uh, my suggestion is that with these batch tests, make note of what you've already passed and you're done with and you can move on with your life, as well as make note of sort of what seems less familiar, what doesn't work the way you thought it did. These badge tests are going to be the same test packets that you'll get back during badge test 2, that you will have your second opportunity to continue working on. So anything that you didn't finish now, you can continue to make further progress on. Uh, so it's good to sort of figure out what didn't you understand the first go around, and what your questions are to get answered between now and our second badge test, which will have more material, but again, another opportunity for this first sort of 2/3 of these badges. Our remaining time, as long as you would like, but if you would like to have an earlier Monday, then I hold nothing against you. The remaining time is open to whatever questions there might be. If there are things you know that you would like reviewed or to go over with me, happy to do that. We can go over problems and things. We can go over lab report stuff. If there are badge test related questions that you ultimately have no idea how to begin, I'm helpful to sort of give you some tips and pointers of where to begin to figure out how to solve these types of problems, things to avoid, things to point you in the right direction, as well as any other questions that might pop up. The last sort of 2/3 of this class doesn't introduce as much material as the first, sorry, the last couple, sorry, the last third of this class does not introduce nearly as many things as the first 2/3. And so these next couple weeks still introduces new material, but it's a good opportunity to catch up, review on things that we may have missed the first time around, and to ask your questions. It's very hard for me to know what exactly you don't understand. It is up to you to figure out what it is that you need help on, and to ask for the help if you would like it. So